Okay.
I see.
Okay.
Yeah, just started.
Okay. The lighting. Light.
Okay.
Okay. Good afternoon. This is a chemistry session for the tutorial. Yeah. Chemistry session for the tutorial. So we are going to look at tutorial sheet 4. Okay, we are going to look at tutorial sheet 4. So yeah. Okay. This is J11. Okay. So we have different questions. We are looking at tutorial sheet 4. So we'll attempt question 10, question 11, then question 12. Okay. So all these they have to be considered. So question 10. Question 10, the question is the energy of a mole of photon of red light from the laser is 175 kJ per mole. Okay, 175 kJ per mole. Calculate the energy of one photon of red light. So what is the wavelength of light? So you need to take note of that. So this is what you have to do. So you're going to say, okay, going to say E. Okay, E is equals to what? 175 kJ. Okay, 175 kJ. So you're going to convert this one. So this is 1 mole times 1 mole. Okay, then this one has to be equated to 6.02 times 10 to the power 23. Okay, so this one will give us 2.91 times 10 to the power negative 22 kJ. Okay. Okay, so we have this one. So this one has to, so we have found now, this one can be converted. Can be converted into kJs, where we just say 2.9 okay, 2.91 okay, 2.91 times 10 to the power negative 19J. Okay, so 2.91 times 10 to the power negative 19J. So you have found, first thing that you have found is you have calculated the energy of one photon. The energy of one photon. So you have calculated. Now you are told to find the wavelength. As you all know, the formula, which is lambda, then you have h c, which is the Planck's constant, and the speed, which is the energy that you have found now. Okay, which is the energy that you have found. Okay, which is the energy that you have found. Okay, I've just switched. Let me switch on to the other marker. Okay, that's better. So we have that. Then HC, okay, over E, okay, So you have got the wavelength, the Planck's constant, you have got so the speed of light, then the energy you have got there. Then since you have got everything, you know the Planck's constant, so you are going to say 6.626 times 10 to the power negative 3 Js. Okay, so let me erase this part. Erase this part. Erase this part. So you have got that one, Js. Then brackets. What you are going to have, we can use the one which is not rounded off. So we have 2.998 times 10 to the power 8 per second, brackets, okay? Then over, you divide by, so you're saying 2.91, the one that you had found, which is times 10 to the power negative 19J. Then you're going to have 6.82 times 10 to the power negative 7 M. Okay, so what would have happened is you have got that one. Now you need to convert, so you're going to say 6.83 times 10 to the power 2, which is nanometer. Then this one should be 683 nanometer. Okay, so we'd have calculated that wavelength of light, red light in meters, in nanometers rather. Then question 11, we are going to question 11 now. So question 10 is done. So we are now going to question 11. Okay, so question 11, that's the one we are going to look at. Okay, we're going to look at question 11 now. Okay, question 11. Okay. Question 11. The most prominent line in the spectrum of neon is found at 865.439 nanometer. Other lines are found at 837.761 nanometer, stroke 87.0162 nanometer, and 878.438 nanometer, and 1885.38 nanometer. So which of these lines represents the energetic light? So question A, this is question 11. They are saying which of the lines represents the most energetic light. So in this case, what you are going to say, the shortest, the one that has got the shortest wavelength. So if we look at the one with a smaller number, the one with a smaller number is the one which is with 837.761 nanometer. So you just say the shortest wavelength. Okay. Then you're done. So now B, what are they saying? What do they want us to calculate? What is the frequency of the most prominent line? What is the frequency of the most prominent line? What is the energy of one photon of the wavelength? So what you're going to say, you're going to start that, which is the frequency, then you have wavelength, okay? So you're going to calculate, you're going to say 2.998 times 10 to the power 8 meters per second over the one which has got less, which was 865.438 times 10 to the power negative 9 m. Okay, so you have got that one. Now you are going to find the value. Okay, you are going to find, of course, the ends will go. So what you are going to have is frequency, which is 3.464 times 10 to the power 14 s. Okay, so you have got that arrangement. Now you have been told to find the energy. You have been told to find the energy. So how are you going to find the energy? So looking at the formula, you have got E is equals to energy, which is EV, okay? That one. So you're going to say the Planck's constant there, you're going to say 6.626 times 10 to the power negative 3 JS, okay? Brackets, okay? Then the one that you calculated, which is the frequency there, you're going to put 3.464 times 10 to the power negative 14, which is S brackets. Then you're going to say, how much is this one? This one should give us 2.295 times 10 to the power negative 19 J. Then you'd have found the energy, just like that. So this is straightforward. Let's look at C. Let's look at C. Let me just erase here so that we look at C. So we have solved. Now let's look at C. Okay, we look at C. We look at C now. So all this is very easy. So we look at C. What are they asking on C? Let's look at C. They're saying what color or colors are these lines? What colors are these lines? So you need to, if you look at this, the answer should be none are, comma, visible light, okay, none are visible light, then comma, or are in IR region. What is this? Is infrared region. Okay, then done. Let's go to question 12. So we are done. So we are done with question 11. We're now going to question 12 of we are in tutorial sheet because what we are looking at is tutorial sheet CH11T4. Okay, tutorial sheet 4. Tutorial sheet 4. That's what we are looking for. We're looking at. So we can erase now. We look at question 12. What does question 12? Question 12 now. Question 12. Okay, question 12. What have they asked? Sketch the energy. Sketch the electron energy level N1 through N5 for the hydrogen. So like we know the energy levels. There are two possible ways. Either you can draw this, can draw a line like this one, okay? Then you are drawing the lines. So this, you look at these lines, okay? So yeah, 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay. I'll skip this one. It's okay. I'll just say. So all this. So we can say this is a N5. Sorry, this is N is equals to 5. N is equals to 4. N is equals to 3. N is equals to 2. N is equals to 1. Okay. So all these are energy level. When an electron is at this stage, this is when an electron is at this stage. This is the ground state. So when it moves, it's occupying the energy level 2. When it moves again to occupy energy level of 3, it moves again to occupy energy level 4. Then lastly, energy level of 5. So this is at one alternative. Then 2 you can also represent by just saying, you draw the lines like this, which is N is equals to 5. Then there you have got N is equals to 4. N is equals to 3. Then N is equals to 2. Then there N is equals to 1. Okay, so you have either you can write this one or that one, we can still give you marks. Okay, So I'll jump. I'll move to question 14. Okay. So I will erase. We are going to question 14 now. Question 14. We look at it. We look at question 14 now. Question 14. Okay, question 14. Question 14. Okay, so question 14. Yeah. So what is question 14? What are they saying? Use the Rydberg equation to calculate the wavelength of the photon. So you have got a photon which was initially at n is equals to 3. Okay, n is equals to, use the Rydberg, how does, okay, n is equals to 3, then question, they are saying, they are referring to question, so question 13. So the energy, so you have got n is equals to 3, then also n is equals to 2, okay? So you have got these two aspects, okay? So what you are going to do is, you know the formula, so lambda is equals to what? R brackets 1 over n final squared minus 1 over n initial squared. So you got brackets. So you have got this aspect now. You are going to replace the values so that now you calculate. So you are going to have 1 over that one. You are going to say 1.0974, okay, times 10 to the power 7, and that one, okay, so Planck's constant. Then you have brackets 1 over, since this is the n final, this is the n final, so what is happening? This is the n initial. So there are two aspects. There are two aspects here where they are saying n is equals to 2. So initially it was at n, so what has happened is this one. If you have this case, you have got n is equals to what? 2, then n is equals to 3. So what has happened is, it was at initially, now it is dropping. So from the, this is the final, right? So you're going to say, since n is equals to 2, then here n is equals to 3. Now what has happened is that it has slightly dropped. So there is, okay, so there is a drop. This electron has dropped. So your, this one will be your n final squared, this one will be n initial squared. Okay, so now you substitute. So you are going to say 2 squared minus 1 over 3 squared brackets. So we need to, we can evaluate together. If you want, you can just say 1 over lambda 1.0974 times 10 to the power 7, that one, then brackets over this one. You can, so if you can solve this one, so we are saying 2 squared, which is 1 over what? 1 over 4, then 1 over what? 3 times 3, which is 9, brackets. Then we have, again, you are saying this one, 1.0974 times 10 to the power 7, m, brackets. So this one, what is a, so you are saying, you can just say, this one can go into, you find the common denominator. The common denominator of 4, what is the common denominator of 4? So you have, what you're saying is, you have, so evaluating, okay, evaluating all of this, so brackets, this one, so this one should be how much? This one should be 25. So 4 times 9, this one should give us a 30 what? 30 something. Let me punch so that we get accurate values. So we're saying 44 times 9, okay, 36. So you can put 36 there. So that 4 into there is 9 minus 4 there. 4 into there is 9, 9 times 1, okay? So 9 into there, it is 4, 4 times, that's why it's 4, like that. So then you're moving. So this entire, you're still moving over 1. The Rydberg there, 9.7, 4 times 10, 7. That one over, which is this one is 5 over 36. If you evaluate everything now, this one should give you the lambda should give you 6.56 times 10 to the power negative 7n. Okay, so this one comparing to the one, so we can therefore conclude that they are the same. Okay, they are the same in terms of calculation. Then you're done. Let's look at question 15. Let's look at question 15. Question 15 now. Question 15. Question 15 now. Okay. Question 15. Okay. Question 15 now. Question 15. Okay. Question 15. So, question 15. So, question 15. What are they asking us on question 15? An electron, okay. Yeah, let me see, question 15, is it? Okay, let's go to, also look at question 15 and 16. Okay. An electron, question 15, an electron moves from N5 to N1 quantum level and emits a photon with an energy of 2.093 times 10 to the power negative 18. How much energy must the atom absorb to move an electron from N1 to N5? What is the wavelength of that? So you have been given, there's a value, okay? So if you have got 2.043 times 10 to the power 18J, okay? You keep this value. So then you say lambda over HC, okay, over A, okay? So you know the Planck's constant, you know the energy there which they have given you, okay, which is how much? This is sorry, it should be 9 there, okay. So you have that one, then you substitute. So it's a matter of substituting. So you are going to say, so they are looking for how much is the energy. So from there, you are going to find the energy. So you have this one, you can say the Planck's constant, you have the wavelength, you also have. So in this case, what you are going to say, since you have this one, so you are going to say 6.624 times 10 to the power negative 34 JS brackets plus what you had, okay? So 2.998 times 10 to the power 8 per second brackets over 2.093 times 10 to the power negative 18 J. Then you have 9.4 times 10 to the power 8 N. Okay, so yeah, Then we look at question 16 now. Question 16. Question 16. Question 16. What do they want? Question 16. So Q16. Q16, what are they saying? An electron moves with a velocity, okay? An electron moves with a velocity of 2.5 times 10 to the power 8 centimeter per second. What is the wavelength? The mass of an electron. What is the wavelength? The mass of an electron is 9.109 times 10 to the power negative 28 grams. So we are going to say there's this formula, which is H brackets mv. So here you are going to say what you have. Since you have that one, you have been given, how much have you been given? So you are going to say this one, you know the Planck's constant, which is 6.626 times 10 to the power negative 34 Js, okay? Brackets over 9.109 times 10 to the power negative 28 grams times 1 kJ over 10 3 grams brackets. Okay, these are conversions because we're only interested in wavelength. Yeah, so times 10 to the power 8 centimeter over 5 brackets 1 m over 100 centimeter. Okay, so this one will give you 2 so give you 2.9 times 10 to the power, yes, because they just wanted the wavelength here, sorry, negative 10, okay, over m over that. So then you'd have solved. Okay, so let's look at question 20. Question 20. We'll look at question 20 now. So that is done. Question 16. We're going to jump. We're going to go to question 20 now. Question 20. Question 20 now. So we are looking at question, so Q20. Okay, Q20, what do they, question 20 now. Okay, question 20, what are they asking for? A photon has a wavelength of 408 nanometer. Determine the frequency, the wave number, the total energy of one mole of such a photon. In what part of electromagnetic spectrum does this wavelength occur? So in this case, we'll start with the first question. So we have got A. A, what are they saying? A, what are they saying? They are saying frequency. So you know, frequency, which is that, you can say brackets, frequency, okay, frequency, which is C over lambda. So looking at what we have, we know speed of light, we can either use, I'll use the one that times, times 8 seconds over, when you convert, because what you have been given, the wavelength you have been given 408 nanometer. So this one to meters, we have what we are calling, what we are saying 408 times 10 to the power negative 9 m. So we have that one. So we can just use it now. We can say 408 times 10 to the power negative m, that one. Okay, so our frequency will be 7.353 times 10 to the power 14 s. Okay, so we have done. So A, we have solved A. We move now to B. B, what is the wave number? Wave number can be represented in 2 angstroms. Angstroms. Of course, there are units. There is a table for units. You need to go through, because there is what we call the angstroms. This unit. Okay. So you need to know that one. So that's what we are trying to answer here. So yeah. So let's go to B. B, what are they saying? B. So I'll erase this part. Then we shall answer B, because B is also very important. So we are on question 20. Now B, what do they want? They are saying the wave number. Okay, so the wave number, the formula for the wave number, we say that brackets wave number. Okay, so brackets 1 over the lambda. So since we have that one, it shouldn't be a difficult thing. What we can do is just 1 over the one that we have converted into meters. That is the wavelength. Then we can place it there, 408 times 10 to the power negative 9 m. So once we have that one, we can now safely say the answer is 2.45 times 10 to the power 6 meters. Okay, you have that one. So B we have solved. We have solved B, which is clear. Now we look at C. What have they asked us on C? So we need to look at C now. C, yes, let's look at C now. So I erase, okay. I can look at C here. Yeah, I can, okay. So this is a B when we have been asked to find the wave number. So that is the expression that has to be done. So let's look at now C. Let's look at C. Let's look at C now. Let's look at C. Okay, let's look at C. Let's look at C. Look at C. Let's look at C. Yeah. C. See what have they asked us? The total energy of 1 mole of such a photon. So the total, let's see, what are they saying on C? The total energy of 1 mole of such a photon. So you are going to calculate. You are going to say, in this case, so we'll calculate in this way. We are going to say, from what we have, we say lambda 408, which is, this is C, 408 times 10 to the power negative 9 m times 10 to the power 10 angstrom. Okay, so this one should be 4080 angstrom. Okay, so that is the answer there. Then we'll look at D. Let's look at D. D, they are saying D they are saying the total energy. Okay, so so let's look at, I think it should even go as far as F, because D they are saying the energy now. So So this should be, so this is I1, then I2 for C, okay? For C, so where they are saying you calculate the total what? Total energy of 1 mole. Okay, 1 mole of such photon. Okay, so what we are going to say, E is equals to H Planck's constant times Na. Okay, the one that we had found earlier. So we are going to say the Planck's constant, which is 6.63 times 10 to the power negative 34, okay, times 7.353 times 10 to the power 14 that we had calculated earlier, then times 6.02 times 10 to the power 23 J per mole. Okay, so once we have that one, we can simply say 2.93 times 10 to the power 5 J per mole, or simply 293 kJ per mole. And we have solved. So all these solutions. So we look at the last one where they are saying, what are they telling us? In which part of the electromagnetic spectrum does the wavelength, in which part of this electromagnetic spectrum does this wavelength occur? So this wavelength occur, so you erase this, this, okay, erase this, okay. So if you are asked to say which the wavelength in what part of the electromagnetic spectrum does the wavelength occur? So this is what you have to do. You have to say it's a visible spectrum. Visible spectrum, we just say violet, so which is 500 nanometer, red, brackets 8, which is 86 nanometer. So what we have is the 408 nm UV. Okay, so we have that one. Now I'll go back to the first part of tutorial sheet 4. I'm sure people are still having challenges, so I'll just make a recap of how best we can assess. Okay, let me just do a recap of what happened. So for instance, if they have given you 3s2, okay, if they have given you 3s2, okay, this represents electrons in the orbital. Okay, this reflects the shape of the orbital. Then this one reflects the principle energy level. Okay, this one reflects the principal energy level. So then the other thing is, people, at least you need to also understand this 1s2, 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. Okay, so then you have also 2p6, 3p6, 4p6, 5p6, 6p6, 7p6. Then you also have what you call 3d10. Then you have also what you call the 4d10. Then also what you call the 5d10. Then also what we call the 6d10, 7d10. Then you start the F's now. 4f14, 5f14, 6f14, 7f14. So I can make this round up. Okay. Okay, so just like that. So I have 1s2, 2s2, 2p6, 3s2. Then from this one, yes, 4s2. Then then 4p6. So of course there are so many things that we can consider here. If for instance we want to draw up you want to write up an electron configuration of, say, sodium. Sodium has got 11 electrons for distribution. So these 11 electrons for distribution, you are going to say, so from here, 1, 2, 3, 4, plus this one, you have how many? 10, plus that one, you should have 12, but you are only required to represent how many? 11. So what you are going to say is 1s2, 2s2, 2p6, then 3s1. Okay, so you have that one. Okay, so you have got that one. So this one is the electronic configuration in orbital form. In orbital form, you are going to say that you are going to say, okay, I'll use above. Okay, since this they have got 3, then you have another one, last one. So we have got the 3 rules that we have to consider. We have got the 3 rules that we have to consider, which are very much important. So I'll erase this part. I'll erase this part. I'll erase this part. So what we are trying to say is we have got 3 rules. We have got the half bar, then we have what we call the Pauli exclusion principle, then we have what we call the Horn's rule. So all these 3, total 3, they help us to solve NHL. So here what we have, we need to fill these electrons singly. So they have got 2 different spins. We have the positive and the negative spin. Okay, so this one represents an electron standing upright. Then this one represents an electron coming downward, which is an opposite spin. So you have this one, so you have there, electrons are filled in orbitals singly before pairing. So you need to observe that one. So that we put in every aspect. So we have that one. So mind you, we have what we call the SPDF. So here the maximum of 2, 6, this maximum of 10, then this is maximum of 14. So you need to know this arrangement. So from there now, you have this, you have filled in singly, now you start pairing. So opposite spin, opposite spin, opposite spin. So how many? 1, 2, so think there. So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is done. Okay. Now we have represented this orbital electronic configuration in 2 ways. We are remaining with the third one, which is the shorthand. You need to know where partly of the orbital electronic configuration is replaced by a specific element. So we can look at one of the elements, which is a neon, which has got 10. So we can say Na, Ne, 3s1. Okay, 3s1. Okay, so we have that one, 3s1. So since we have this arrangement, 3s1. Now, provided we have N plus, this element has undergone ionization. Typically we are saying the first ionization. So in this case, we are going to say, so there has been an elimination. Initially we have 11 electrons, but we remove 1. So therefore we remain with 10 electrons. Okay, we remain with 10 electrons that we have to distribute on the arrangement here. So we have 1s2, 2s2, 2p, 2p6. Yeah. So if you want, you can say 1s2, 2s2, 2p6, just like that. That's another version. Okay. So orbital diagrams, as usual, we can write them. Okay, so we have that one. So we can distribute, These are uniform, so of course all of them will be paired, And that's the thing. So all you know, you need to know this aspect. Then the other thing that the notable thing is that you need to know definitions are also important under this same tutorial. That's you need to know some. So as a summary, we know quantum numbers. We have the principal quantum numbers, and we have the angular, which is n, quantum number, okay, which is L. Then we have the magnetic quantum number. Okay, so we have, this is MS. So all these students are required to know definitions of this, because we usually ask. Yeah, so these are very much cardinal in terms of consideration. Consideration. Then the other aspect is you need to know how to, you need to know, just from the previous calculations that we are doing, this is a set you need to know, of course. Just you need to understand that most of the things that have been aligned, they are tallying with the lecture notes that you are always provided with. So I urge you just to continue studying hard and ensure that you are going through your books such that you are able to pass your exams, because you just have a few weeks which you'll be able to sit for your exams. Then next week you are meeting Mr. Nonde or Mr. Mianza. That is on Tuesday 16 to 17. Be able to go through. Sure, by then we'll have what we are calling tutorial sheet 5, based on how far the lectures have gone. So you'll be able to appreciate and also learn more ways of solving the other tutorials that will be produced. So from me, Mr. Mambwe, I'm saying goodbye. Enjoy your day. Ensure that you continue studying, you continue keeping the momentum, ensure that you are doing the right thing every day. So have a blessed day and goodbye. Thank you.